11th grade portions.
So basically waves and sound is done, and then thermodynamics also.
Yeah, and then properties of matter and fluid dynamics.
Properties of matter, fluid dynamics, everything is done.
Yeah.
Okay. So how much time have they spent on all of this? Like
Uh,
how many weeks has happened? In
I'm not sure.
thermodynamics, how much time did they spend approximately? When did they start?
We did thermodynamics before properties of matter and
Okay.
fluid dynamics. So
Okay. So what was the last topic that was done? Fluid also is done.
yeah,
Yeah.
What was the last topic that was done?
for me, it was
Uh,
properties of matter.
okay. Okay.
Yeah, it was properties.
Okay, fine. So for physics, what we'll have to do, no, is I will do like like one or two extra classes going forward every week. Okay.
Yes.
Yeah.
So like today we'll doing physics. Tomorrow we'll do chemistry. Tuesday or Wednesday, I want to do physics again.
Yeah.
So Tuesday or Wednesday, decide a time, sometime in the morning, anytime in the morning, and all will be fine for me. Whatever is convenient to you guys. Okay.
Yeah.
So going forward, we'll do one extra class till we catch up or go ahead, right?
Yeah.
Yeah.
So because we are behind in physics. Chemistry, what is going on for them? GOC.
Yeah, GOC and
Yeah. So
isomerism. So we finished it. So
Okay. Okay then.
that is stop.
And maths, where are you guys?
maths we finished,
Yeah, finished
hyperbola.
hyperbola and that's it. Stop.
Hyperbola.
Yeah, we
Okay.
finished.
Calculus has not started.
No, not for me.
Okay. Okay. So we were right now doing sound waves, I think. So sound waves exercises and all have you guys done?
Yeah.
Yeah.
mm,
HCV have you guys done? Sound waves? No.
Completely.
I don't think you would have done. No? You would not have had time only.
Yeah.
So have you read the theory, the whole theory?
Yeah.
Yeah. Yeah.
I think we
Okay.
started doing and then we stopped. So with that much.
No, we had in the class, we had done till like interference of sound waves, basic reflection of sound waves till there.
Yeah.
I think we have
Yeah.
to do air columns and all,
Yeah,
vibrations of
that's
air
it.
columns and all. But while you were doing waves and sound with Alan, what happened? What did you guys do there?
Yeah, so I did till the thing we did it, I did the exercise for HCB like little bit. Then I
Uh,
left it there only since the exam started.
so, but this waves
And
and sound would have been covered way back, right?
yeah,
Yeah.
In Alan, when the chapter was being done, how much work have you put in? Like, what have you done? Alan book,
Yeah. The book only.
but that would not have been finished, right?
no, only unit exercise.
Only a few sections you have done.
No, I learned the main exercise is almost all done.
Main exercises, as in exercise 1, 2, whatever you have done,
Yeah.
finished everything.
Yeah.
Okay.
And the exercise at the back end of the book.
But at CV, you have not done.
No, I think we started it like before we stopped.
I know
So
about what we did, dude. I'm asking when you were studying in Alan, this particular topic, did you do HCV?
oh no, no.
Right, it's-
Okay. Okay. We will start with the standing longitudinal waves. Before that, we'll do reflection of sound waves, that section. It's on page number 336.
Yeah.
Reflection of sound waves. So the important thing here to remember is just like when plane waves, when a traveling wave, which is transverse traveling wave on a string,
Yeah.
that encounters a boundary, Boundary as in there's a heavy string and then there is a light string, right?
Yeah.
So as soon as you encounter a boundary, you are encountering a change in medium. This medium we had discussed, this medium will be heavier. So it is going to be, mu is higher, right? For this,
Yeah. Yeah.
mu1 is greater than mu2. Mu by mu, I mean mass per unit length. So, so velocity of sound is going to be lower, right?
Yeah.
Is less than v1 is less than v2.
V2.
So this is called a denser medium
Yes.
because speed of sound is lower, and this is called a rarer medium, right? Or speed of wave is lower,
Yeah.
right?
Yeah. Yeah.
Not sound, just a wave. Speed of the wave is lower. And when you go from denser to rarer medium, right? Denser to rarer medium, reflection, what happens during reflection? Will it will it get inverted or not?
No, it won't. Denser to rarer, it won't.
So if it enters a region where wave velocity is larger, so here wave velocity is larger, right?
Yeah.
Yeah.
Then there is no inversion. So denser to rarer, there is no inversion in the reflected wave. And similarly, if it was rarer to denser, then in the reflected wave, there was an inversion.
Yeah.
Yeah.
In the reflected wave, there is inversion. This is very important because by inversion, what do we mean? By inversion, we mean a phase change of pi or something.
Right.
Yeah. Yeah.
Phase change of pi. Because if you add pi to the wave equation, it will become negative, right? Y is equal to minus a sine, it will become, right?
Mm-hmm.
So that will mean that for the same t and x, your wave will be downward. That is an inversion, right?
Yeah.
Yeah.
Why are we discussing this? Because when sound wave is going to propagate also, it will encounter different types of mediums, right? And as soon as it encounters different types of mediums, it may or may not undergo a pi phase change. Correct?
Yeah.
So if it undergoes a pi phase change, then you will have to, the resulting wave that comes back will be having a slightly different equation, right? It will not be the same type of equation.
Yeah. Yeah.
Yeah.
So eventually what we want to understand is what happens when it interferes and all, like it interferes with another wave. So what will happen to the resultant equation? So we have to be careful about this phase change stuff when you encounter a different medium. Also, in any of these situations, transmitted wave always is same phase. There's no inversion, right? Doesn't matter whether it is denser to rarer or rarer to denser, right?
Yeah.
Yeah.
So now look at this section. He says, when there exists a discontinuity in the medium, the wave gets reflected. When sound wave gets reflected from a rigid boundary, the rigid boundary means fixed end types, right?
Yeah.
Yeah.
The particles at the boundary are unable to vibrate. They cannot move because they are fixed, right?
Yes.
Thus,
Yeah.
a reflected wave is generated, which interferes with the oncoming wave to produce zero displacement at the rigid boundary. So you can think of the junction like one wave has come here. One actually it should be a compression and rarefaction pulse. So I'm drawing it like this. One wave is coming here. Now, if it is a rigid boundary, this point cannot really move, right?
Yeah.
So
Yeah.
how will you cancel the displacement of a wave coming in from the forward direction, right? It wants it to move. So how will you cancel that? You will cancel that by imagining a backward wave coming from this direction and both of the waves simultaneously hitting and canceling it.
Yeah.
Like you are basically imagining a reflected wave that comes from the opposite direction, okay? And because of the reflected wave, this particular displacement and this particular displacement get cancelled, right?
Yeah.
Yeah.
And after that, a reflected wave has to pass like this, right?
Yeah.
Correct. So that is what he is saying. Thus, a reflected wave is generated which interferes with the oncoming wave to produce zero displacement at the rigid boundary. At these points, zero displacement, the pressure variation is maximum, because we know that pressure and displacement are shifted by pi by 2 phase, right?
Yeah.
There is a pi by 2 phase
Hmm.
difference between the pressure wave and the displacement wave. So if you're saying that the displacement is zero, then the pressure variation is maximum, right?
Mm-hmm.
Right. Yeah.
So now what he says is, thus a reflected pressure wave has the same phase as the incident wave. Basically what it means is, a compression pulse will go back as a compression pulse only, and a rarefaction pulse will go back as a rarefaction
Right.
pulse. So this is happening when you encounter a fixed end. When you encounter, this is what happens. There is no change. A compression pulse gets reflected as a compression pulse. Rarefaction pulse gets reflected as a rarefaction pulse, right?
Yeah.
Now, the slightly different thing will happen if it encounters a low pressure region. What is a low pressure region? Is when you have something open to the air or something, right?
Mm-hmm.
Right. So when the wave reaches an open end, it gets again reflected. The force on the particles there due to the outside air is quite small. Hence, the particles vibrate with increased amplitude. So now, if you are at an open end, you are free to move around, right?
Yeah.
You
Yeah.
are free to move around, but what is not free? Pressure cannot change. Suppose a wave has been generated, and this is an open end, right, of this tube.
Yeah.
Now, this open end is open to the atmosphere entirely, right?
Right.
Yeah.
Yeah.
So, a tiny wave in a small tube will not change the pressure of this point.
Yeah. Correct.
Okay, it cannot, because it's exposed to the whole atmosphere, right?
Mm-hmm.
Yeah.
Yeah.
It will be able to move. Displacement is possible, but change in pressure has to be zero, right?
Yeah.
Mhm.
Yeah.
Correct.
Yeah.
So open end, basically, pressure there remains at the average value, he's saying. As a result, the force on the particles there due to the outside air is quite small, and hence the particles vibrate with increased amplitude. As a result, the pressure there remains at the average value. That means change in pressure is zero.
Zero. Yeah.
Thus, the reflected pressure wave interferes destructively with the oncoming wave. So, change in pressure is zero. That means whatever pressure change was this wave was trying to do has been cancelled by this change, right?
Mm-hmm.
Yeah.
Like some reflected wave you have to imagine that comes from this side and cancels the pressure variation, right?
Yeah.
Yeah.
Correct.
Correct. So a reflected pressure wave is interfering in destructively with the incoming pressure wave, right?
Yeah. Yeah.
Yeah.
There is a phase change of pi in the pressure wave when it is reflected by an open end. So basically
Okay.
now realize that obviously a pressure wave, it is a wrong diagram like this, but just for the heck of it right now, just think about this. If a pressure wave comes like this with a positive amplitude, you have to have a pressure wave like this which comes,
Yeah.
right?
Yeah.
Which has to cancel this pressure change, right?
Yeah. Yeah.
Right.
So finally, the reflected pressure wave will come back like this, right?
Yeah.
So it is clearly a pi phase change.
Okay.
Pi phase change in pressure wave, right?
Yeah.
Mm-hmm.
So now what you can think is that a compression pulse basically will come back as a rarefaction pulse. Rarefaction is converted to compression. Compression is converted to rarefaction after reflection.
Mm-hmm.
If you encounter a free end, free end by free end means free to move, free to be displaced.
Mm-hmm.
Fixed end was where displacement was not possible, right?
Yeah.
There is no change in pressure, no, right?
Yeah.
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 No, there is no change in displacement. There is a change in
Displacement.
pressure. Pressure can change there, right?
Yeah. Yeah.
If displacement is zero, pressure variation can be maximum also, right?
Right. Right.
Okay, so this will become important later. As soon as we do standing waves and all, it is important there. So let's see what standing longitudinal waves are. So what we are going to do is replicate the theory of standing waves when we saw in waves on a string. So standing longitudinal waves, and we are going to think about how they help in the vibrations of air columns. Vibrations of air columns are what happens in most of the musical instruments that you see. So flute or any musical instrument like this has an air column, and that is vibrating, and that is what is creating the sound, right?
Yeah, yeah.
So what he starts off with, he's saying two longitudinal waves of same frequency and amplitude. He's taking P1, P2, P naught sine omega t minus x by v. All of this is familiar stuff, right? So as soon as two waves, one wave is P naught sine omega t minus x, omega t minus kx, and another wave is P naught sine omega t plus kx. These are waves going in opposite directions. If these two waves interfere, the resulting wave will be given by the principle of superposition, and you just have to add the two equations, right? So once you add, you'll get 2 p naught cos kx sine omega t, right?
Right.
This is the interference of these two waves. So this looks like an SHM again. This looks like an SHM with different amplitudes, right?
Yeah.
So basically, you will have some points where there will be nodes and some points where there will be antinodes. Nodes will be the point where the pressure variation is zero, right? And antinodes will be the point where the pressure variation is maximum, right?
Yeah.
So this is similar theory that was there earlier also, right? So in particular, at certain points, the pressure remains permanently at its average value. But basically that means is this P that we are writing was actually excess pressure, right? It's not total pressure, it's excess pressure, pressure above the average value. Pressure above average value. So if this P is zero, that means excess pressure is zero and the overall pressure remains at the average value, right? Correct. So there are some points where this 2 p naught cos kx is permanently going to be zero. Those are called pressure nodes. Nodes. And there are some points where it is equal to 2 p naught, right? Those are pressure antinodes. When cos kx is 1, right? So the distance between any two consecutive nodes or antinodes is lambda by 2. This is normal stuff which we have seen before also, right?
Yeah.
If there is a pressure node somewhere, think of it as a displacement antinode, because pressure and displacement are pi by 2 shifted, right? Pi by 2 phase difference between them. So pressure node becomes a displacement antinode, pressure antinode becomes a displacement node, right?
Yeah.
So these things you need to know. Now he talks about the closed organ pipe and stuff. Closed organ pipe and open organ pipe, right? So closed and open organ pipe. So by closed organ pipe, what you mean is one end is closed, right?
Yeah.
It cannot be both ends are closed, okay? That will not be a very good organ pipe. Right? Then you cannot do anything. So open organ pipe is both the ends are open. Closed organ pipe is a cylindrical tube having one end closed, right?
Yeah.
So what happens here? Sound waves are sent in by a source vibrating near the open end, right? So near one open end, you are sending in sound waves from this source. Somewhere source is here. You're sending in sound waves. Now, as it comes and strikes this end, there is a reflection, and reflected waves and incoming waves will now interfere, right? So eventually you will have a situation where standing waves can be generated because you're sending incoming sound waves and they're getting reflected and coming back also, right?
Yeah.
Okay. So now what he's saying is, see, after, so this inverted wave, so ingoing pressure wave gets reflected from the fixed end. This is a fixed end, right?
Yeah.
Correct. So this reflected wave again gets reflected at the open end, right?
Okay. Yeah.
Mm-hmm.
Correct.
Yeah.
Okay, fine. So here it will come back and again get reflected, right?
Yeah.
So now
Right.
think of this wave which has had two reflections, right?
Yeah.
And think of the new sound wave going here, new sound wave which has had no reflections, right? Now
Mm.
eventually these two waves, right?
Yeah.
These two waves will interfere wherever they meet, right?
Yeah. Right.
Correct. So wait, I missed the sentence that he's mentioning. Correct. The twice reflected wave. Okay. He's saying after two reflections, it moves towards the fixed end and interferes with the new wave sent by the source in that direction. The twice reflected wave has traveled an extra distance of 2L,
12.
right?
Yeah. Yeah.
So whatever is this L, the twice reflected wave has traveled extra 2L.
12.
So
Yeah.
phase difference between this and this will be 2 pi by lambda into 2L, right?
Right. Yeah.
Because 2 pi is the phase difference for one lambda distance, right?
Yeah. Correct.
Yeah.
So 2 pi by lambda into 2L is the phase change between this and this. However, there is also a reflection at an open end here, right?
Yeah.
Mm.
Reflection at open end on the top causes an extra phase change of plus pi, right?
Okay.
Reflection at the fixed end didn't cause any change. We saw earlier that it compression comes back as compression.
Yeah.
Rarefaction comes back as rarefaction. But
Yeah.
reflection at open end inverts it, right?
Yeah.
Mm.
Correct.
So compression becomes rarefaction. No? So that pi part you have to take into account, right?
Yeah.
So the waves, these two waves will now, this wave and this wave will now interfere constructively only if the phase difference is a multiple of 2 pi, right?
Okay.
Right. So
Yeah.
4 pi L by lambda plus pi
So,
should be equal to 2n
2
pi,
Yeah.
right? This is for constructive interference here, correct?
Right. Yeah.
Yeah.
And if this happens, then we can simplify this and write L is equal to 2n minus 1 lambda by 4,
Yeah.
right? So
Yeah.
for constructive interference, you have to have L is equal to 2n minus 1 lambda by 4, where n can be any integers, right? So obviously this is an odd number type of a thing, right? So you can also
Yeah.
write it like 2n plus 1 lambda by 4,
Yeah.
because you just start from a different n, right?
Mm.
So basically n can be 0, 1, 2 here,
Yeah. 0 and 2.
right? So for constructive interference to happen, you have to have length of the closed organ pipe to be multiples of lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on, right?
Yeah.
Yeah. Yeah.
Then you will have constructive interference
Constructive.
at that particular wavelength, right?
Yeah. Yeah.
So now see what he's saying. In such a case, the amplitude goes on increasing until the energy dissipated through various damping effects equals the fresh input of energy from the source. So right now you are having constructive interference, and obviously then the amplitude will become double, right?
Yeah. Yeah.
Yeah.
And this will keep happening, and energy will keep rising, right? But obviously it cannot rise forever because there are other effects like damping and friction and in the air and so on, right?
Right.
Yeah. Yeah.
Which causes a loss in energy. So eventually what happens is the damping energy that is lost will equal the energy that is provided by the source.
Okay.
So you will have basically, as the source sends in waves, basically it is sending energy, right?
Yeah.
Mm.
It is sending energy to the system, to this air column system, right?
Yeah.
Yeah.
So you cannot have a situation where it is sending energy, but suddenly amplitudes are rising constructively, right? Interference is happening and it is becoming bigger and bigger energy, right? It will not go on forever because obviously there is friction and losses here. So
Yeah.
eventually at some point, what will happen is the losses will equal the extra energy that is coming in. So you will have a high amplitude system, like you will have a constant amplitude that will be fixed, right?
Yeah. Yeah.
Now, such waves exist in both the directions and they interfere to give standing waves of large amplitudes in the tube. The fixed end is always a pressure antinode. So think about it, fixed end has to be a displacement node, right? It cannot move there. Displacement node, therefore it is a pressure antinode. And the open end is a pressure node. Pressure cannot change at the open end because it is open to the atmosphere,
Mm-hmm.
right?
Ah,
So it
yeah.
is a displacement antinode.
Antinode. Yeah.
In fact, the pressure node is not exactly at the open end because the air outside does exert some force on the air in the tube. So this is an end correction sort of a thing. It's not exactly at the top end, it is someplace else, above or below, right? But we will ignore that for now. The condition for having standing waves in a closed organ pipe is given by equation 16.14. So this equation only.
Yeah. Sure.
Standing waves condition is this, and this is L is equal to 2n plus 1 lambda by 4. So now obviously frequency will become divide the velocity by the wavelength, right?
Yeah.
Velocity by wavelength. So now wave velocity, so wavelength,
E
for
by
wavelength
4L.
you can write 4L by 2n plus 1, right, is equal to
Yeah.
lambda. And as soon as you put that in, you will get the equation 2n plus 1 V by 4L. That is the frequency,
Yeah.
right? So now you can see that there are only certain frequencies that are allowed in a closed organ pipe.
Right.
You will have V by 4L, 3V by 4L,
3V by
5V by
4L.
4L, and so on, right?
Yeah.
Hmm.
The lowest one is called fundamental V0, and upper frequencies will be called overtones, right?
Yeah.
First overtone is 3V by 4L, right?
Yeah.
Upper frequencies are also sometimes called harmonics, and you will see here that basically any multiple of the fundamental is called a harmonic, right? And
Yeah. Yeah.
here all odd harmonics are only possible.
Right.
Only
Yeah.
odd harmonics are possible. Even harmonics are not possible. They will not generate standing waves, right?
Okay. Yeah.
So standing waves is the situation where you will have large amplitude waves in the system, and that is what you will be able to hear and detect and all properly. So ultimately, these are the frequencies that are possible in an instrument like this. V by 4L, 3V by 4L, and all, right?
Right.
Yeah.
Yeah.
Now, if you look at the figure here, this figure 16.9, it is very important because it shows two different types of figures. The first three graphs are pressure graphs, okay?
Okay.
And the last three graphs are, what below that is a displacement wave graph. So he has started with on top. If you look at the first three graphs, the first condition is pressure node at the top, right?
Yeah.
Yeah. No,
And display pressure antinode at the bottom. So that distance is lambda by 4 right now. Between a node and an antinode will always be lambda by 4.
Lambda by 4. Yeah.
So in this case, L must be equal to lambda by 4.
Yeah. Yeah.
Right?
Yeah.
In the other case, see, it is node to node, that is lambda by 2, and then node to antinode, that is again lambda by 4, right?
Yeah.
Yeah.
So it will be lambda by 2 plus lambda by 4. So that is 3 lambda by 4 is the total length,
Yeah.
right?
Yeah.
So that is for the 3V by 4L situation, right?
Yeah.
You should know basically where pressure nodes will be, where pressure antinodes will be, so that you can draw a rough diagram like this. In a particular question that is given to you, you should be able to draw a rough diagram like this,
Yeah.
where you have N, A, and lambda, and distances should be accurate.
Okay. Yeah.
Number of nodes and all you should write properly. Now, the graph just below the top graph is the displacement version of the same wave. So if you see every place where there is a pressure node, there is a displacement antinode. And every place where there is a pressure antinode, displacement node is there.
Yeah.
Right?
Yeah.
Otherwise, everything is the same. Both the versions of the standing wave are correct. It's just that we will focus mostly on the pressure ones for sound.
Okay.
but it's fine to think of the displacement node also. It's okay. Then we have open organ pipe. Again, same thing, but this time there is open at both ends, right?
Yeah.
So open at
Yeah,
both
yeah.
ends. So obviously there will be pressure nodes at two ends,
Yeah.
right? So
Yeah.
so there is a cylindrical tube now, and there is pressure nodes at two ends, right?
Hmm.
So think about it. If you do the same process as before, and if you send a wave from the top, right, it gets reflected once at the other open end, and then comes back and gets reflected at this open end also, right?
Yeah. Yeah.
And then interferes with the new wave that was sent by you, right?
Yeah.
So there is a 2
Yeah,
pi phase
yeah.
difference. No, one
Yeah. 2
wave
pi. Yeah.
was sent like this, it gets inverted and comes like this, then gets inverted again, right? So
Hmm.
now it
Hmm.
sort of looks like the original wave only, no?
Yeah.
Yeah,
So the
yeah.
only because pi here and pi here, right?
Fine. Yeah, yeah.
So the only phase difference is going to be due to the 2L extra distance, right?
Hmm.
Yeah,
There
correct.
will be no plus pi. The plus 2 pi doesn't count, right?
Yeah. It
Yeah,
doesn't
yeah, it
count.
doesn't count.
So this 4 pi L by lambda is the only thing that matters, and that should be 2n pi, right? For constructive interference,
Yeah.
Hmm.
Hmm.
right? And so you get L is equal to n lambda by 2.
Yeah, okay. Hmm.
L is equal to n lambda by 2 for an open organ pipe, right?
Yeah.
And therefore frequency will become n v naught by 2L,
Mm-hmm.
right?
Okay. Yeah.
So the fundamental will be v by 2L. Then after that it will be 2v by 2L, 3v by 2L, and so on, right?
Yeah. Yeah.
Okay. Yeah. Hmm.
And in this case, all harmonics are possible, right?
Yeah.
All
Right.
harmonics
Huh.
are possible. All multiples of v naught by 2L are possible, right?
Yeah, yeah.
Correct. So basically, the sound from an open organ pipe will have more frequencies available to you than the sound from a closed organ pipe,
Closed. Yeah.
right? So
Yeah.
that's why sometimes instruments which are open at both ends sound better. The sound
Mm-hmm.
quality is richer, right?
Okay.
So
Yeah.
Hmm.
you can possibly see examples, like for example, if you look at the mouth organ, right? Mouth
Mm-hmm.
organ, if you have seen, right, harmonica, the tiny one,
Yeah.
Yeah. Yeah.
so that is closed at one end, because one end is, there are holes, but one end is closed and one end is open. But for example, the flute, right?
Hmm.
Mm.
Flute. Yeah.
Flute is open at both ends. You are sending in sound from one source, and there is a hole there at the other end also,
Mm.
Yeah. Yeah.
Yeah.
right? So flute sounds are better rather than
Yeah. Okay.
flute sounds are better rather than the harmonica sounds. It is
Okay.
shriller in the harmonica because lesser frequencies are available. All
Yeah.
frequencies are
Hmm.
not available, are available for the flute. So that is just side stuff, but the idea is that you can draw graphs like this. Now see the graphs a b c there in 16.10, right?
Hmm.
Yeah. Yeah.
So node at the two ends, which is a pressure node at both the ends, right?
Hmm.
Yeah.
And distance between any node and node will be lambda by 2, right?
Lambda by 2. Yeah.
So this length of the air column in part A of the graph will be L is lambda by 2, right?
Hmm. Hmm.
Okay. uh, okay, so basically this part should be fine. Then we have determination of speed of sound in air, the resonance column method, and Kunz tube method for determining the speed of sound. These are experiments, and it is important to know both of these methods, but I will leave it to you. It's not very difficult. Resonance column method, just read this. Both of the methods, please read, okay?
Yeah.
Because what happens is these days they have started asking experimental style questions in advanced. Kunz tube also, please read. Mark it as important, okay? Important for advanced. It might not be important for JEE mains, but knowing what is going on and how you measure speed of sound, this is an experimental setup. You just have to read it, you will understand. basically read it and be able to understand why the equation 16.20 is derived. Right?
Yeah.
It's not difficult at all. You can understand it. But mark it if nobody has told you. This is important for advanced. Okay.
Okay. Yeah.
Experimental type of questions have started being asked, and they might give you a paragraph where there's actually it's about resonance column method only, and you have to analyze it and solve a question based on that, right? So you need to be aware of that. The next important section is beats. Okay, so beats. So what are these beats and all? So what happens here is, so far whenever we were doing interference of waves, right, we were interfering waves which had same frequency and all, right?
Yeah.
We had one wave which was like this, P1 is equal to P naught, and another wave was also omega was same, right?
Yeah.
Something like this we had interfered for standing waves, no?
Mm-hmm.
However, what happens, suppose we are seeing the interference of two waves going in the same direction. We could have PO1 and PO2, different amplitudes, right? So normal interference here would be just the superposition of these two waves. You just do this, right?
Yeah.
So you will get that root of P naught 1 square plus whatever, right?
Yeah. Yeah.
This is the result that you get. There is no phase difference, so it is just 2 P naught 1 P naught 2, right? Because cos delta is 1, because
Yeah.
delta is not there, phase difference is not there, right?
Yeah.
So this is the normal interference, but many times in nature situations are such that the frequency of the two interfering waves doesn't have to be the same, right? So what happens if the two waves that are interfering have slightly different frequencies? That is what we are going to study. So if one of the frequencies is omega 1 and one of them is omega 2, right?
Yeah.
So then the equation becomes much more complicated, okay? You cannot just now randomly simply add, right?
Yeah.
Because this sine term is different from this sine term. You have to think about what to do now, okay?
Yeah.
So first, we are going to focus our discussion on situations where omega 1 and omega 2 are different, but not very different.
Yeah.
So are not equal, but the difference mod omega 1 minus omega 2 is small compared to the magnitude.
Okay.
So basically, this difference is small as compared to the actual magnitude of the frequency.
Yeah.
Okay.
Okay.
Yeah.
Yeah.
So you could have a situation where some wave is 400 hertz and another wave is 404 hertz, right?
Yeah.
So the
Yeah.
difference 4 hertz is quite small compared to 400.
400. Yeah.
So that is the situation that we are going to think about right now. Okay.
Yeah.
Yeah.
So let's say one wave is P is equal to P1 sine P naught. Now we are going to assume equal amplitudes but different frequencies, basically. Omega 1
Right. Yeah.
T minus Kx and omega 2 T minus Kx. P is equal to P naught sine omega 2 T minus this K will also be different because that is omega 1 by V, right? And
Yeah.
this is omega 2 by V, right?
Yeah.
So
Yeah.
this is the situation. Now see what he has done. He is just adding P1 and P2. He's just adding P1 and P2, and he's using only one new variable. So I will not write it like this actually, because it's easier if you just keep one new variable, omega 1 T minus X by V, right?
Yeah. Yeah.
The different variable, the variable that is not equal, should be as few as possible, right?
Yeah.
Speed of the wave in the medium is the same because medium itself is the same, right? Both
Yeah.
waves
Yeah.
are traveling in the same medium, right?
Right. Yeah.
So V is same and all, and the difference is because of the omega 1 and the omega 2, right?
Yeah.
So he takes P naught common and he simply adds psi C plus psi D.
Yeah.
P naught common, and you're adding sine of omega 1 t minus x by v plus sine of omega 2 t minus x by v,
Expertly, yeah.
right?
Yeah.
So now sine c plus sine d is 2 sine c plus d by 2. So c plus d by 2. So what will you get? Omega 1 plus omega 2 t minus omega 1 plus omega 2 x by v, right?
Yeah.
By 2, right?
Yeah, yeah.
And cos c minus d by 2,
It's
right?
possible.
Yeah.
So it will become again omega 1 minus omega 2 t, and
Yeah,
it will become minus omega 1 minus omega 2 x by v by 2, right? Something like
Yeah.
this,
Yeah. Yeah.
correct?
right, right.
So you can take omega 1 plus omega 2 common outside here, and you'll get 2 p naught sine of omega 1 plus omega 2
Yeah.
by 2 into t minus x by v, and here cos of omega 1 minus omega 2 by 2 into t minus x by v, right?
Right.
Hmm.
Yeah.
Correct. So now think about it. Since what we will write it as, we'll write omega 1 plus omega 2 by 2 is the average of the two values, right? Will
Yes.
Right.
almost be, will we call it as omega, because
Okay. Yeah.
it will be close to
Yeah.
either one of them, right? Because
Yeah.
omega 1 and omega 2 are not very different from each other, right?
Mm-hmm.
So we'll call that
Yeah.
thing
Yeah.
omega, and we'll say 2 p naught sine omega t minus x by v, and cos of delta omega, change in omega, right?
Mm-hmm.
Like
Change in
omega,
order.
let's call
Yeah.
this delta omega, difference in the frequencies, right?
Mm-hmm.
Delta
Yeah.
omega by 2 t minus x by v, right?
Right.
Yeah.
Right.
Correct.
Yeah.
Now, now this situation resembles an SHM equation if you focus on this part. This is the SHM part, okay? And
Yeah.
this comes in the amplitude, right?
Right.
2 p naught into cos of this is the amplitude,
Mm-hmm.
and a sine omega t minus kx, right?
Yeah.
That looks like a normal wave, right? Not SHM, normal traveling
Normal.
wave,
Yeah.
right?
Yeah.
So what we get is, as a result of interference of these two waves, we are getting a new wave which is something like this.
Mm-hmm. Okay.
Something like this. This is the amplitude of the wave, and then there is a sine omega t minus x by v, right?
Yeah.
This is the
Yeah.
a, and this is the sine, right?
Mm-hmm.
Something like this, right?
Yeah.
This is a new traveling wave. But what is so weird about this traveling wave? The difference in this wave is that the amplitude of the wave is varying,
Mm-hmm.
right? The amplitude of the wave is varying with the position, right?
Yeah.
Yeah.
Varying with both t and x, right?
Yeah.
Right.
Now, how fast is this varying, right? Think of this variation. This variation is itself a wave type of variation where
Right.
the frequency is del omega by 2, angular frequency, right?
Yeah. Yeah.
Yeah.
Angular frequency is del omega by 2. And here, the wave itself was going at a frequency of omega, right?
Omega. Yeah.
Correct. Now,
Yeah.
because we have assumed earlier that del omega is small, we can say that this variation is very slow as compared to this variation, right?
Right. Right.
As compared to this.
Yeah. Yeah.
Because the frequency W or omega is much higher than this, right?
Yeah.
Yeah.
Because the difference is very small, no, this del omega by 2, right?
Yeah. Yeah.
Correct. So what he's saying here, after 16.22, he's saying as W or omega is greater than del omega by 2, the term A, this term A varies very slowly with time as compared to sine omega t minus x by v, right?
Yeah. Yeah.
Thus,
Right.
we can interpret this equation by saying that the resulting disturbance is a wave of angular frequency average value, right? See,
Okay.
resulting disturbance is a wave of angular frequency W, right?
Yeah.
this was omega 1 plus omega 2 by 2, right?
Right. Yeah.
Basically, what we are saying is if 400 hertz wave and 404 hertz wave combine, the resulting will be a 402 hertz wave, but not a regular 402 hertz wave. It is such a wave whose amplitude is also varying, and varying at a frequency of del W by 2, right?
Yeah. Yeah.
2 hertz,
2 hertz. Yeah.
right? Something like that, right?
Yeah. Yeah.
Correct.
Right. Yeah.
So he's saying that only. He's saying thus we can interpret this equation by saying that the resultant disturbance is a wave of angular frequency omega is equal to omega 1 plus omega 2 by 2, whose amplitude varies with time, right?
Right.
And
Right.
is given by 16.22. This is how the amplitude varies with time, right?
Yeah. Yeah.
Yeah.
Now he's saying as a negative value of amplitude has no meaning, the amplitude is in fact mod of A. So actually this is a pressure variation and all. So you don't have negative pressures and all. So what you will be saying is this mod of this is the amplitude of this wave, right?
Yeah.
Hmm.
Yeah.
So mod of A is what really matters here. So if you look at the graph of any function, so look at figure 15.6, 16.16, okay?
Right.
So 16.16 is tracking A values, okay? So A
Hmm.
values can go from 2 p naught to minus 2 p naught, right?
Yeah.
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 And let's say you draw the function, draw the graph of this type of function, this 2 p naught cos omega, del omega by 2 something, right? So
Yeah.
it looks like a wave like this, right?
Yeah. Yeah.
But if you take the mod of that, right, mod of A will mean basically that you have to take a reflection from the point where it goes below the x-axis, right?
Yeah. Yeah.
Yeah.
So the actual wave will look like this, right? So now
Hmm.
Right.
notice that the frequency of this B part graph is double of that, right?
Correct.
Frequency of the B graph is double, or period of the second function is double, half of the period of the first function.
Yeah.
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 The first function varies at 2 pi or something. The second function only at pi. After pi, it will repeat,
Yeah.
right?
Yeah. Yeah. Yeah.
So if you say that my overall wave is an average wave of 402 hertz, you will say that its amplitude is not varying at 2, but at 4, right?
Hmm. Yeah.
Amplitude is
Yeah.
varying, amplitude is mod of A. So therefore, that variation is at 4 hertz, right?
Yeah.
That is
Yeah.
simply del omega by 2 multiplied by 2, right?
Multiply by two. Yeah. Right.
Correct. So
Yeah.
basically now you have understood what beats is. This phenomenon where you have a varying amplitude wave that forms as a result of the interference of two waves with slightly different frequencies, right?
Yeah.
Hmm. Hmm.
That wave is called that phenomena of this happening, this interference happening is called beats, okay?
Okay.
Yeah.
And the variation in amplitude happens at a slow rate. Variation in amplitude happens at a slow rate, which is equal to the difference in frequencies of the original waves, right?
Yeah.
Yeah. Yeah.
Slow, and happens at change in frequency, right? Difference in frequency of the original two waves, right?
Yeah.
Right.
But the actual resultant wave that happens as a result of superposition goes off at the average frequency, right?
Right. Yeah.
Like actual waves frequency is 402, okay?
400. Yeah.
Correct.
Yeah.
So now he's, let's go back to the previous paragraph. He's saying let us concentrate our attention to a particular position x and look for the pressure change there as a function of time, okay?
Yeah.
At a particular position x, he is trying to think of how pressure changes with time, right?
Hmm. Hmm.
Yeah. Yeah.
Equations 16.21 and 22 tell us that the pressure oscillates back and forth with a frequency equal to the average frequency W of the two waves, but the amplitude of pressure variation itself changes periodically between 2 p naught and 0, right?
Yeah. Yeah.
Correct.
Yeah.
Yeah.
So now in this figure 16.15, he's drawing the plots of both A and B. B is the sine part, A is the amplitude part, right?
Yeah.
And
Yeah.
then
Yeah.
he is drawing below that, he's drawing the product of these two functions. Okay.
Hmm.
Yeah. Yeah.
So first he's drawing 2 p naught sine omega cos delta w by 2 t minus x by v, right?
Yeah,
So
the
notice
amplitude.
that is varying very slowly, there's not much fluctuation there in the first part, right?
Yeah, yeah.
Yeah.
But in the
Slowly.
b part, sine omega t minus x by v, it is varying quite fast, right? The
Yeah,
fluctuations are
correct.
very, because its frequency is much higher, right?
Yeah. Yeah.
D goes from -1 to 1. The A part goes from -2 p naught to 2 p naught, right?
Yeah.
Yeah.
Now, multiplying these two functions together, you will see sort of this graph, which is an envelope of the overall thing, right? So,
Yeah.
so overall function becomes like you can just check any point, right? Check a point which is at say 2 p naught, and at that point what is b, and multiply those and get the product thing, right?
Right.
Yeah,
And
yeah.
plot it there, right? So you can do it yourself also, but this is the overall graph of the wave. Now notice that uh, its overall profile is limited by the 2 p naught to -2 p naught, right?
Yeah, yeah.
But its frequency is slightly higher than that frequency, obviously, right?
Right. Yeah.
And amplitude is diminishing to 0 and then rising again to 2 p naught, right?
Mm-hmm.
Right. Right.
Correct. So that is the basic understanding that you need to have. It's fairly easy if you pay attention to what he has written here. Okay. So now he talks about variation of intensity at a point. He's saying amplitude delta A oscillates between 0 to 2 p naught with a frequency which is double of the frequency of A, right? This is because
Yeah.
as A oscillates from 2 p naught to -2 p naught, the amplitude A mod A covers full oscillation from 2 p naught to 0 to 2 p naught again, right?
Mm-hmm.
Right.
This we have already discussed, so there's nothing very difficult here. So he says by equation 16.22, the frequency of variation of A is del W by 2 divided by 2 pi.
Divided
Okay?
by 2. Yeah.
Yeah.
Thus, frequency of amplitude variation will be double of that, which is del W by 2 pi, right?
Yeah.
Mm-hmm.
So del W by 2 pi, take the 2 pi inside. W1 by 2 pi is frequency 1, and W2 by 2 pi is frequency 2, right?
Yeah.
Yeah.
So it will be simply mod of F1 minus F2, right?
Yeah.
So now notice that we have written this frequency as mod of V1 minus V2. So what is the meaning of that? It is the difference between V1 and V2 with which the amplitude oscillates. Amplitude is oscillating with that frequency,
Right.
and
Right.
wave is going ahead at a different frequency, higher frequency, right?
Yeah.
Yeah.
This
Yeah.
phenomenon of periodic variation of intensity of sound waves. So intensity of sound waves depends on the amplitude square. So if amplitude itself is changing, then obviously intensity is also varying, right?
Also changing. Yeah.
Yeah. Yeah.
So that phenomenon is called beats. So one cycle of maximum intensity and minimum intensity is counted as one beat.
One beat.
So
Okay.
frequency of the beats is F1 minus F2 mod. Okay.
Yeah.
Now go to the next page, second paragraph. He's saying the phenomenon of beats can be observed by taking two tuning forks of the same frequency and putting some wax on the prongs of one of the forks. So loading with wax decreases the frequency of a tuning fork by a little. Okay.
Right.
Yeah.
So one of them is slightly less frequency than the other, right?
Uh-huh.
Now, if you hit both of them at the same time, then the waves that will come out will interfere to form a beat sort of a situation,
Right. Yeah.
right?
Mm-hmm.
When these two forks are vibrated and kept side by side, the listener can recognize the periodic variation in loudness of the resulting sound.
Yeah. Yeah.
Like,
Yeah. Yeah.
like at times it will seem louder and at times it will seem very faint, the resulting sound.
Yeah.
Right.
So,
Yeah.
and that varies. Like it becomes louder again, becomes faint again, becomes louder again, which is not something that you would expect. What you would expect
Yeah.
in a normal situation, if you had sent two waves of equal frequency, you will get an equal, some common amplitude and all. No?
Yeah. Yeah.
Yeah.
Amplitude will not change. What will change is the phase and all, right?
Mm.
So
Uh-huh.
now the next thing that he says is, for beats to be audible, the difference V1 minus V2 should not be very large. An average human ear cannot distinguish the variation of intensity when it is more than 16 times per second. So you should have mod v1 minus v2 should be less than equal to 16 for us to be able to detect it.
Right.
Yeah.
So beats will not happen. I mean, audible beats or something that we can detect cannot happen at a difference greater than 16 hertz.
Yeah.
Mhm.
Yeah.
Yeah.
Okay. Then the last thing that we have to cover is Doppler effect. Doppler effect is pretty straightforward. Here, we are not going to do the diffraction part 14.12 because we'll do that in light when we do light.
Oh,
So
okay.
right now, diffraction of sound is not so important. Light, it is important. So we will go to Doppler effect. Doppler effect is very straightforward. It is about how when, for example, if you're at a railway station and the train is approaching, it sounds very shrill. And as soon as it crosses you, it sounds a lower frequency, right?
Yeah. Yeah.
You would
Yeah.
have seen that. I mean, I have definitely seen that.
Yeah.
When
Yeah.
train approaches, it sounds shriller. When it crosses you, it sounds heavier. The voice, the sound becomes lower in
Yeah.
frequency. So why is that happening? That is happening simply because when there is an observer and a source, observer is whoever is listening, source is the source of the sound, right?
Mm-hmm.
If they
Yeah.
are moving relative to one another, then the what the source creates frequency f, right, or
Yeah.
f
Yeah.
naught, that is not what the observer hears, because when the observer, how does an observer detect a frequency, right? Like for
Mhm.
example, if I'm standing somewhere, how will I judge whether this sound is higher frequency or not, right? So
Mm.
in my ear, the way I detect frequency is I get one pulse of sound at some time, say t is equal to 0, right?
Yeah.
Yeah.
One pulse has come and the next pulse comes at t is equal to delta t, let's say, for me, right? The
Mm-hmm.
next
Right.
wave arrives at delta t. Then what I am saying is that the time difference between two pulses is delta t. So frequency will be, for me, frequency observed will be 1 by delta t, right?
Yeah.
Yeah. Yeah.
So that means that many pulses are coming per second, right?
Yes. Yeah.
Correct. So my
Correct.
observed frequency depends on the time duration between two pulses that reach me, right?
Mm-hmm.
Yeah. Yeah.
So obviously, if the source is moving, then the two pulses will reach me depending on how it is moving, right?
Yeah.
Yeah. Yeah.
So suppose the source created a wave and sent a wave, right, with some sent a pulse at some time, right? And
Mm.
Hmm.
source is stationary right now, suppose, then it will cover some distance d in some time t, right?
Yeah.
And the next pulse it will send after a time interval dictated by this f naught, right?
Mm-hmm.
The source is creating pulses at this frequency, no? So 1 by f naught is the time interval when the next pulse was created, right?
Yeah.
Yeah.
But if both of them are not moving, then this is going to remain the same, no, the time interval when I see the second pulse.
Yeah. It'll be same.
Right.
Yeah.
Yeah.
Like the first pulse will reach at some time and after the same time interval another pulse will come, right?
Yeah.
If both
Yeah.
source and observer are not moving,
Not moving. Yeah.
and if any one of them is moving, then it will be different. It
Mm-hmm.
will depend on
Right.
how fast someone is moving, right?
Yeah.
Yeah. Yeah.
This time interval that I detect will be different based on who is moving which way and whatnot, right?
Yeah.
Yeah.
So now you can read it, it's very obvious. Now suppose let's do the first case. Observer is stationary and source is moving, right?
Mm.
So the observer is that ear that is marked in figure 16.18. Source is moving s, right?
Yeah.
So source s is moving and it had released a wave at time t is equal to 0, right?
Mm.
And the
Right.
distance
Right.
between the source and the observer was x initially, right?
Yeah. Yeah.
Correct. So now time taken for this wave to reach me would be x by u, right?
Mm-hmm.
Correct.
Yeah.
X by u, no, not u, x by v. V is the speed of
Right.
sound,
Yeah.
right? X by v is the time taken for this pulse to reach me.
Oh,
Yeah.
uses
Correct.
Yeah.
the yeah. Okay.
Now,
Yeah.
now the source itself is moving at u, right?
Yeah. You. Yeah.
So after some time capital T, right,
Hmm.
where f is equal to 1 by t, right?
Yeah.
After some time capital T, where t is equal to basically 1 by f, the source releases the second pulse, right?
Yeah.
Correct.
Correct. Hmm.
So in that time, the source has moved a distance of u into capital T.
Yeah. Yeah.
So the distance to be covered by the second pulse is simply x minus u capital T, right?
Yeah.
Correct. The second pulse will
Yeah. Yeah.
reach me after covering this much distance, right? So
Yeah.
it will
Yeah.
take a time of x minus ut by v.
Yeah.
Yeah.
Also, already t time has passed, right? When it
Mm-hmm.
was created, right?
Yeah.
Yeah.
So I will hear it at time t plus x minus ut by v, right?
Yeah.
I will receive the second pulse at this time, right?
Hmm.
Yeah.
And I received the first pulse at time x by u, right? X
Yeah.
by
Yeah.
v. X by v is the first pulse reached me, right?
Yes.
Yeah.
Yeah.
Correct.
And second pulse reached me this at this time, right? So
Mm-hmm.
the difference of time between the two pulses is what matters for my observation of frequency, right? So if you
Yeah. Yeah.
take the difference of time, this minus this, if you do, or what is coming, t minus ut by v, right, plus x by v minus x by v. This is the delta t for me, right?
Yeah.
Yeah. Yeah.
Right. So
Hmm.
my observed frequency is 1 by delta t. So 1 by t minus ut by
UT
v.
by V, yeah.
Yes.
So
Yeah.
you will write it as vt. So it will become v by v minus u into t, right?
Mm-hmm.
So it will become v
Yeah.
by v minus u. 1 by t is the f of the original source, right?
Yeah. Yeah.
So f naught is v by v minus u into f, right? You understand?
Yeah. Yeah.
It's
Yeah.
not very difficult at all. Like you just have to think about source, observer, source creates sound
Yeah.
at frequency f1 by t, right? So it creates sound at t is equal to 0, that reaches me at time t is equal to x by v, right?
Yeah.
This is the first pulse. And
Yeah.
second
Yeah.
pulse, it creates at time t is equal to capital T after one time period, right?
Hmm.
So that time it was somewhere here. The distance is actually now x minus ut, right?
Yeah.
Because it is moving towards me, right?
Yeah.
And it was created at this time, so that much time has already passed. So now I will hear it at what time? T is equal to x minus ut
X
by v
minus UT.
plus
Plus
t.
T. Yeah.
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 So I am hearing the second pulse at this time, first pulse at this time. So my frequency, my time lapse between the two pulses is simply t ut by v, right? Delta t for
Yeah.
me.
Right. Yeah.
Mm-hmm.
That
So my frequency is v by v minus u into f naught, right?
Yes. Yeah. Yeah.
That is fairly easy. If you have a situation where he's moving away, you will replace this with x plus ut, and frequency will be v by v plus
V
u
plus U.
f naught, right?
Yeah.
Mm-hmm. Yeah.
Right. So again, source stationary, observer moving. You can read it again. Same thing, no difference. Okay.
Ah.
Okay.
Ah.
Yeah.
So you can read this section. The overall thing is summarized in 16.27. Okay. So 16.27 says frequency is equal to v plus u of observer by v minus u of source into frequency of the source, right?
Right.
Yeah.
So how do you remember this without making mistakes? You remember this by common sense. U observer by v minus u source into frequency original, right? Or this is the
Hmm.
source frequency, right?
Yeah.
Yeah.
So so think about it. Think about it using common sense. If something approaches you, like a train approaching you, right? It should
Mm-hmm.
Yeah.
sound higher, right?
Yeah. Yeah.
Ah.
Correct. suppose put yourself as if you are a stationary source, a stationary observer, right?
Okay, yeah.
So my observer part should be 0,
Zero,
and
yeah.
and source part should be something. So you cannot put plus u source, then it will become lower, no?
Yeah, it'll become lower, yeah.
So it has to be minus u source, right, in the denominator,
Yes, yeah.
correct? So
Yeah.
Yeah.
only thing you have to remember is observer is on top and source is on the bottom. The observer
Right.
velocity is on top and source velocity is on the bottom. That's all that you have to
Yeah.
remember. If you remember that, then just think about the train coming towards you should give higher value, so it has to
Yeah.
be minus us, right?
Yes,
Yeah.
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 And if I'm running away
Going
from the
away.
train, it should be lower. It should be uh, if observer itself is source is stationary, I am running away, right?
Yeah, yeah. So it'll be
Correct.
minus u
One
if
second.
observer's running away.
Observer is running away. So it will be minus u, right?
Yeah,
And if
yeah.
I'm running towards it, it will be plus, right?
Plus, yeah.
Yeah.
So on top should be plus, right?
Yes,
Yeah.
yeah.
So just remember the logic of it. And if you are in doubt, think about the time interval between two pulses that you hear.
Mm.
Like,
Yeah.
think about whatever is the situation. Think about when will the first pulse come to you, and after that, when will the second pulse come to you. Just measure the time. Actually, the difference between the pulses will dictate the frequency that you hear,
Yeah, yeah.
right?
Mhm.
So that point should be clear to you. Sometimes you could even have accelerated motion in this case, okay? So
Right.
even if something accelerates, again, don't worry about formulas there. Think about when is the first pulse going to reach you, and even if source is accelerating and all, what happens after that? When is the second pulse going to reach you, right?
Yeah.
The
Okay, yeah.
difference in the two times will dictate the frequency that you hear. If this is the difference between the two times, frequency observed for you is 1 by delta t,
Right.
Mm-hmm.
Yeah.
right?
Yeah.
So
Yeah.
questions could be difficult, or you can try to make the question difficult by making someone accelerate and stuff, right? But
Hmm.
then don't try to learn any formulas for that. Just do the common sense thing. Like just
Right. Yeah.
take t is equal to 0 at the time when first pulse was created, and you will hear that at some later time, right?
Yeah.
And then
Yeah.
second pulse was created at some time by the source, and then it will reach you at some later time. You have to just measure these values, right?
Right.
Okay, yeah.
Yeah.
Once you do that, this will be fine. Doppler effect is this, then musical scale, sonic booms, these are easy, like you can just
Oh,
read through it. There is not much there. We are done with the chapter, but you have to do the exercises, okay? There are so many exercises
right.
for a reason, because people get confused in many of these things. So I want you guys to try
Right.
as
Right.
many as possible. Like 89 questions are there. Many of them will be quite interesting. So definitely try all of them. Like especially from 2030 onwards, you should try everything. Okay.
Yeah.
Okay. Okay.
Till 2025, I think will be so quite straightforward. But after 25, you can see that questions will become interesting.
Mm-hmm.
You should try everything here.
Yeah.
Uh, we will do another physics class on Tuesday. Okay.
Okay.
Just
Yeah.
Yeah.
set up a time. We will continue. We'll not discuss problems on Tuesday. We'll go ahead to the other chapter theories that
Okay.
we are behind. We will discuss problems
Right.
of
Right.
this chapter on like maybe next week or something. Okay.
Okay, yeah.
Okay. Okay.
Okay. That's all for now, then.
Sir,
Hmm.
like, for revising the whole year's portions,
Hmm.
do you think HC Verma will be enough for physics? Or do
Uh,
we have to go through all the Allen textbooks also?
What are you trying to revise it for? Depends.
Like
If
an
you are
advanced
revising for
level
Allen
exam?
exam, then you should go through the Allen textbooks. But
Okay, okay.
like uh, Allen exam is not so important. Okay. If you are revising for JEE, right? JEE advanced and all, if you are thinking of that, then you should go through HCV for sure.
Okay,
Mm.
yeah.
Like you should have brief notes, or you should mark it in your book, the important sections and stuff, and you should go through the HCV book in detail. Like even at
Hmm.
the even at the expense of doing some extra stuff. Like these days, there might not be, like, I think the Kunsttube thing is not technically in the syllabus, but even at the expense of doing some extra stuff, it is important to know everything in HCV, know everything here. So
Mm-hmm.
uh, for Allen exam, I don't know. For Allen exam, I'm sure you have to revise your Allen booklets,
Right,
Okay,
right.
yeah.
but because they will ask something directly which will be there in the
Direct
booklet,
questions, yeah.
right? So, but for JEE Advanced, if you are thinking about everything in HCV is important, you have to know it. Okay,
Yeah,
so
Yeah,
yeah.
yeah.
theoretically, you need to know everything in HCV. Even the questions you should be aware of, because some difficult question in the HCV exercise can come as an objective. These days, they've started asking slightly harder questions. So
Okay, okay.
exercises also, the important problems that you have seen, should sort of know. I know how to solve this. It is there in HCV. Like you need to have that much clarity and that much recall of the textbook. Like I know, for example, question 86 of rotation, I will always be able to solve because I've done it. 86 and 85 of rotation. Like you
Hmm.
have to be able to recall the question by their numbers.
Okay.
That is the level of preparation and thoroughness that you need. Like that is what is required. Okay, so I
Yeah.
mean, question 45 of rotation chapter also I know, because that is a nice question with a sliding rod and stuff. So
Okay.
things like that, you need to do it so thoroughly. Okay,
Right.
so
Yeah.
I mean, when you are revising the overall thing right now, focus on the new chapters that we have not yet done. Those chapters you have to read. Like if it has been done in your Allen, right,
Yeah.
Yeah.
and you have not done HCE, then your preparation is incomplete.
Right. Yeah.
Like fluids and all, properties of matter, fluids, thermodynamics. I don't know how much you have read HCV.
Yeah. Yeah.
So if you have not done HCV, it is not going to be working. It's not going to happen. I mean,
Right. Okay.
you need to spend more time on it. Even if they are not focusing on the book, no, like you have to know everything in this book. Questions are
Yeah.
asked directly every year. Direct questions from HCV come. Okay, so
Okay, yeah.
there is no doubt that you have to go through this. So for now, focus on this. Once we are done with the syllabus, I will do things from other books. So
Right.
I
Right.
have some sources that I want to try out with you guys. Like with other batches, I've not gotten the time to, because it was already delayed. But we will be able to finish in time, and I want to practice some slightly higher level books also. So
Mhm.
so but we have to finish it first. Okay, so
Yeah.
Okay, yeah.
and and this is basic and this is paramount. Like you need to know this much, only then we can do ahead anything
Yeah.
more.
Yeah.
So
Right.
make sure that right now you don't get distracted by any other book and all. Don't worry about DC Pandey or whatever other books are there, right? Like there are many books in physics, but ultimately you need to know one thing really well.
Yeah.
Yeah.
Your Allen booklets can be your extra source, but right now only focus on HCV. Make sure that you know everything there.
Yeah. Yeah.
Okay, yeah.
3-4 months down the line, 6 months down the line, when we are done with everything, then we'll look at other sources also, and we'll try to expand our knowledge.
Yeah. Yeah.
The same chapters we'll do revision. Like this whole thing we'll revise. Like assuming we are done with say July, August physics, hopefully we'll be done with July, August types. After
Mhm.
that, we have time from then on to January to prepare from, or actually till next May, because I'm thinking of advanced mostly. So
Right.
JEE mains, so you will have to focus on NCRT plus HCV.
Yeah.
Okay, yeah.
So for JEE mains, again, the focus will be on NCRT more and HCV after that.
Yeah.
And that is what you will have to prepare in December, November, December, January. But
Hmm.
JEE advanced, which is May next year, for that, we have time from August, September onwards till May. And we have to do other things also, because the standard of questions is becoming harder. Have you guys looked at 2019 or 2020 JEE papers advanced?
Uh,
Rishi, have you looked at it?
Not advanced. I think mains lecture.
Mains, nobody cares, dude. We are not preparing for mains in these classes, guys. You guys
Yeah.
realize that, right?
Yeah.
Like I am not interested in mains, man.
Right. Yeah.
Even if I'm not teaching you, you guys will do well in mains.
Right. Right.
Mm.
Your level is not to prepare and worry for mains, okay? And that
Yeah.
is not my goal. So let's focus always on advanced. Look at the 2019 2020 advanced papers. They're quite tough.
Right. Right.
You should look at it, at least look at it. No, now next year you will write that exam, right?
Yeah.
Yeah.
Look
Yeah.
at it and see the questions. 1 year syllabus is almost over for you. No, no.
Right. Yeah.
Mm.
So half the paper should, or 40% of the paper you should be able to see.
Yeah.
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 Go through the 2019 2020 papers, keep the printouts at your place, go through them so that you realize what is the level that you need to attain.
Yeah.
Okay. Yeah.
Yeah.
Don't be clueless about it till October, November, and then you'll be like, I have to prepare for mains. And then actually, many people actually look at advanced papers only when March is done. March, they start preparing.
Mm.
And that is
Mm.
too late. No, how will you prepare?
Right.
You
Yeah.
have to look at advanced papers. Forget about mains. I mean, at least for now.
Yeah.
Mains we'll focus on October, November, December. That is enough, dude. It's very easy.
Yeah. Okay.
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 So
Yeah.
look at advanced papers and look at what level they are asking and what you have to prepare. Look at it
Yeah.
from math, physics, chemistry, all of the subjects. You will realize where the gaps are and how much you need to prepare when you have a look. Okay.
Mm-hmm.
Mm.
Okay. Yeah.
So take a printout. Everything is available online. JE advanced
Yeah.
papers are there
Mm.
everywhere, right?
Yeah.
So just take a printout, keep it with yourself.
Yeah.
Okay. Yeah.
Tomorrow we'll do chemistry, Tuesday we'll do physics, and we'll do more of physics classes in the coming weeks
Physics.
to cover up everything.
Okay.
Okay.
Yeah.
Okay.
Yeah.
Bye.
Yeah.
Bye, sir.
Mm.
That's